we're getting it done. We've got Edexcel Sample Assessment Materials, Paper 2. So this one is still pure mathematics. So luckily there's no messing about with a large data set or anything like that yet. So I'm just going to crack on. First few questions should be pretty quick. I'll stick the chapters at the bottom of the video because it's probably going to be a long one. Right, let's have it. So question 1 says f of x equals all of that, so some cubic. And we can see that we've got these unknown coefficients here in A. Given that x plus 2 is a factor of f of x, find the value of the constant A. So, it's the factor theorem, right? So factor theorem is basically saying, right, if x plus 2 is a factor, then f of minus 2 is 0, right? So f of minus 2 is 0. Basically just sub it in, a few marks, and we're done. So what we're going to get, we're going to get 2 times minus 2 cubed minus 5 times minus 2 squared. Let me get in here. Here we go. Right, I'm ready now. Plus ax, so that's going to be minus 2a, and then plus a. All of that's going to equal 0. We just got an equation. Where's my calculator? It's here. Might need this. Or I might not. Who knows? So minus 2 cubed is going to be minus 8. Times that by 2, we're going to get minus 16. Minus 2 squared is going to be 4. Times that by minus 5, we're going to get minus 20. Minus 2a plus a, well, that's just going to be minus 1 lot of a, equals 0. Right, let's stick this a onto this side. So we're going to get a equals minus 16 minus 20. So I reckon that's going to be minus 36. Cool. Question 1, done. See, this is what we like. We're getting it in, no messing. So, some A-level students were given the following question. Cos theta equals 2 sine theta. Cool. The attempts of 2 of the students are shown below. Okay, so they like getting you to do this. We're basically just going to have to identify mistakes. Okay, identify the error made by student A. Okay, so they have cos theta equals 2 sine theta. Well, that's no error. They're just copying out the equation. And then they say tan theta equals 2. So what is the student kind of trying to do here? Well, I suppose they're trying to use that trig identity, aren't they? They're trying to use the trig identity that is tan theta. But what is this trig identity? Well, it's sine over cos. So let's have a think. Given this, does it make sense what the student did? I'm not sure it does. Because if I was to have cos theta equals 2 sine theta, well, if I wanted to get a tan theta out of this, I would divide by cos theta, wouldn't I? Because tan is sine over cos. So what I would then say is I would say, okay, well then cos over cos is going to be 1 equals 2 sine over cos, which equals 2 tan theta. So I would actually have tan theta equals a half. Well, that's not what they have. They have tan theta equals 2. So I think the student thought that tan was actually cos over sine. If tan was cos over sine, then I would divide by sine. So I think the fact that you've done this is probably, the examiner knows what you're on about at this point, but try and give them some words. And it doesn't need to be some absolute beautifully crafted sentence because they really get what you're on about at this point. I would say, look, I don't know, I could say, student thought that tan equals cos over sine, something like that. I mean, come on, tell me that the examiner doesn't know what you're on about if you've done all of that maths and you've told them that. So I reckon that's fine for part A. Student B gives theta equals minus 26.6 as one of the answers to cos theta equals 2 sine theta. Explain why this answer is incorrect. Okay, so there's a few ways I could do this. The simplest, actually, you could just sub the value into the equation and see if it works, right? So get your calculator out. Why not? Why don't we just literally go, my calculator's in radians. Make sure it's in degrees here, because this is in degrees. I want you to do this every time you're ever touching trigonometry with your calculator. So I'm going to quickly whap that over to degrees. And now I'm literally just going to write, look, well, the left-hand side of this equation is going to equal, cos of minus 26.6, which is going to equal, stick it in your calculator, this old thing here, 0.894 ... And then the right-hand side is equal to that. And then, obviously, if those two sides aren't equal, then it's not a solution, is it? So the right-hand side is going to equal 2 sine of minus 26.6, which is going to equal 2 sine minus 26.6. Yeah, exactly. Look, it's minus 0.8955 dot dot dot. They're not equal, are they? So there is not going to be a solution in minus 26.6. Cool. So I didn't even need to look at what student B did to get that at that point. Explain how this answer arose. Now I would have to look. Okay, so let's have a look at what they do. They have cos theta equals 2 sine theta. Cool. They then square both sides. Now this is interesting because that's actually kind of getting another equation. So we kind of know that when we square root things, so if I already have the equation x squared equals 4, okay, then to solve this equation, I would say, okay, well, that would imply that x, and then I would say, when I square root, I need to do a plus or minus. And I would have plus or minus 2. That is because both of these solutions satisfy this equation, okay? But if I already had, I suppose the equivalent of what they're doing is as following. They've got the equation x equals 2, okay? So that equation, x is just equal to 2. That is the only solution. They then square it, so x squared equals 4. But this is interesting, because if x is 2x squared equals 4, correct, but x squared equals 4 doesn't just imply that x equals 2. So this has two solutions. This here has one solution, right? Just x equals 2. This has two solutions. So here's the thing. If we start with the equation with two solutions already, then it makes sense to say x equals plus minus 2. But if I start with an equation that just has one solution, you can see how squaring it would actually get more solutions that I didn't initially want. Because now if I was to kind of try and, solve this, I would get x equals plus minus 2. Well, that doesn't make sense at all, does it? So you really need to think about where you're actually starting here. Yes, when we square root things, we want to do a plus minus, but are we allowed to square it in the first place, if that makes sense? So the point where they square the equation, they're actually going to be introducing new solutions here. If their initial equation was cos squared equals 4 sine squared theta, then yes, it would be a solution because they've not introduced any new ones. But the initial equation was just cos theta equals 2 sine theta. So we actually have to be a bit careful here. When you square equations, you actually think, wait, am I introducing any new solutions that I don't want here? So it would basically just be like, look, it's when they squared both sides. Both sides of the equation, basically, yeah. That is how it arose. And I reckon that's enough for part 2. Okay, question 3 says, given that y equals x times 2x plus 1 to the 4, show that, okay, so find the derivative. So this is two things multiplied together. It's an x and then the 2x plus 1 to the 4. When we have the product, or two things multiplied together, the way we differentiate it is the product rule. And then there might also be a tiny bit of chain rule thrown in here. I don't think this question is too problematic if you can remember those two things. So product rule basically says, look, differentiate that times write down that plus write down that times differentiate that. That's it. So what do I mean by that? So some people like to kind of write it out beforehand. I'm just going to go straight in because this video is going to get long, so I want to be quick. So essentially I'm going to write down the x and then I'm going to differentiate the 2x plus 1 to the 4. So this is actually going to be the chain rule here. So what we're going to do is we're going to first of all differentiate the inside function here being 2x plus 1. So the derivative of the inside function is 2. And then we're going to treat the inside function kind of as if it's an x. In other words, we're just going to differentiate the outside function. So the outside function is essentially like this x thing, or 2x plus 1, to the 4. So to differentiate that, I would be 4 times x, or in this case 2x plus 1, cubed. So that's how I go with chain rule. You might do it kind of more longhand, writing out u and v and stuff like that. This is how I do it. It's quite quick because I've got a lot of practice. And then basically we go the other way. So I've written down the x, differentiated that, so now I need to differentiate the x, so that's going to go to 1, times write down the other thing, so 1 times 2x plus 1 to the 4. That's it. Just clean it up at this point. So this is going to be 8 times x, so 8x times 2x plus 1 to the 3, plus 1, so 2x plus 1 to the 4. Looks like I can take a common factor of 2x plus 1 out here, so I will do that now. Not just 2x plus 1, actually. 2x plus 1 cubed. because this is a 4, this is a power of 3, so I can actually take that out. What's that going to leave me with? It's going to leave me with 8x here, times 1, and then plus, well, just one lot of 2x plus 1 now. Okay, so just simplify what's inside the bracket, and I think that we will be laughing. So 8x plus 2x is 10x, and then stick a 1 on the end. And then, yeah, so A is going to be 10, and B is going to be 1 in our case R, and N is going to be 3, it looks like. Sweet, done. I love it at the start of the paper when you're just popping off questions rapid. So let's keep it going. So on question 4, it says f of x is e to the x, and g of x equals 3 ln x. Find an expression for g f of x. So the way I like to think of this, I think it helps if we actually put more brackets on it. If I put another bracket around f of x here, now it kind of tells me what to do. It's basically saying, look, well, what's f of x? I can sub that in. That's e to the x. So then all I do is I just work out what g of e to the x is. So in other words, we start on the right and go to the left. Like we put f into g. But if you write the brackets, it kind of just falls out for you. So all I'm doing is I'm just swapping the x with an e to the x here. Now ln and e, they're inverses of each other. In other words, they're going to cancel each other out. So ln of e to the x is just going to be x. So that's part A. Easy as, mate. Right. Part B says should there was only one real value of x, which gf of x equals f g of x. Okay, well we've already worked out gf of x, haven't we? If we were to work out fg of x and then just stick it equals the answer for part A, we're going to get an equation, try and solve it, see what happens. So fg of x, what's that going to equal? Well, we just do the same thing, so it's going to be f bracket of g of x. What's g of x? It's 3 ln x. So stick 3 ln x instead of the x in the f. So it's going to be e to the 3 ln x. Now, I said that kind of ln and e's are inverse and they cancel each other. They do, but we have to be careful. They need to be fully touching, right? So here, I can't quite cancel them because there's this 3 just in the middle of them. This 3 needs to get off, basically. Is there any way that I can just get this 3 to get off? I can use the power law here. Because this is next to a logarithm, I can stick this 3 up in the power of that log. So I can say that this is instead e to the ln of x cubed, x to the power of 3. Now look, the e and the ln, they're together and they can cancel. So I'm just going to be left with x cubed here. So I mean, this is the other side of my equation, right? So the equation that I now have to solve is just 3x equals x cubed. I'm going to take this 3x onto the right-hand side, just stick everything equal to 0. So I'm going to get x cubed minus 3x equals 0. Take a common factor of x out to get x times x squared minus 3 equals 0. What now? Well, we either have x equals 0 or x squared minus 3 equals 0. This equation here would imply that x squared equals 3, which implies that x equals plus minus the square root of 3. So at the moment I'm thinking, okay, haven't I just got 3 real solutions? So it's at this point where 2 things could have happened. You made a mistake somewhere, or there was something in the question that actually tells you, oh no, wait a minute, only this one's valid. So I hope I've not made a mistake. I might have done, but I'm going to check the question first. If the question doesn't have anything like that, I've probably messed something up somewhere. Okay, let's have a think. Look at how these functions are defined. Specifically g of x. Look at the domain of g of x. It says that x has to be greater than 0. So look at this here. I've got 3 values of x. I've got minus root 3, 0, and positive root 3. But wait a minute. X has to be greater than 0. So that's not valid, and that's not valid. Therefore, my only real solution to this equation is just going to be x is equal to the positive square root of 3. Another little one, this is what we like. The mass m grams of a radioactive substance T is after being first observed is modelled by the equation m equals 25e to the minus 0.05t. According to the model, find the mass of this old chestnut 6 months after it was first observed. Well, we just sub t equals 6 in, right? No. So I don't think this question's that hard, but I think the one thing that they might be thinking that you could mess up on is just kind of using the wrong units for t. Look at this. T is measured in years. So they want you to go, oh, wait a minute. what would the value of t be after 6 months? It's going to be a half, isn't it? Because there's 12 months in a year. So you just sub t equals a half, and that's all you do. So m is going to be 25 e to the minus 0.05 times by a half. Stick it into your calculator, no worries. So we're going to get what? E, can't find the E button, think I'm going mad. There it is. E to the power of minus 0.05 times by a half, which is going to be 24.3827 ... Let's go 3 sig fig, so it's going to be 24.4. Fantastic, and that's going to be in grams, isn't it? Cool. Part B says find the derivative. So again, chain rule. Chain rule is basically like I've got a function inside another function. So in this case, the thing I need to differentiate is this e to the minus 0.05t. The inner function, I would say, is the minus 0.05t. So the first thing I do is I differentiate that inside function. So that's just going to be minus 0.05, isn't it? And then I differentiate the outside function. So the outside function is basically just like e to the t here. And that always goes to itself. So it's just going to be e to the minus 0.05t. Am I done? Not quite, because it's still at 25 chilling at the front. So 25, don't write that, because that would be 25 minus that, right? That, which is 25 multiplied by this. So really, equals km, where k is a constant to be found. Okay, well, what's m? M is basically this exact thing, but without this. So if I was to rewrite this, I'm not even going to work this out. I'm just going to write minus 0.05 multiplied by 25 e to the minus 0.05t. Why have I done that? Because that's m, isn't it? So this is just going to be minus 0.05m. So k is just minus 0.05. Look at that. Another one. Question 6. What is that? All right. Complete the table below. First one's done before you. State if it's always true. Okay. I'm not going to write it in the table here because with the whiteboard it's just going to be annoying. But I'll just kind of do each part as its own question and we can talk about it and I'll tell you the answer. So basically, the example I give in is about a quadratic equation having 2 real roots, and they're saying it's sometimes true because of the discriminant, right? Cool. So it might be a bit proofy, this. We'll see. So when a real value of x is substituted into a quadratic, the result is positive. So, I mean, you could just start subbing values in, but I think you might be here a while. What we like to do here is we complete the square. Because when we complete the square, we have a squared number plus another number, and we can say, well, wait a minute, a squared number is always greater than or equal to 0, so then it depends on this, whatever this other number is. So I'm going to complete the square on this. So it's x squared minus 6x plus 10, so I'm going to half the coefficient of x. Then I'm going to minus this number squared, and then I've got the 10 chilling on the end. So look at what this is equal to. This is a squared number plus 1. Can this thing ever be negative? No, because this bit here is always greater than or equal to 0. 1 is obviously positive, so this whole thing is actually greater than or equal to 1. Therefore, this thing is actually always true, isn't it? Because, like, tell me a value of x I can stick in there that's going to get me a negative number. There's nothing, is there? Because no matter how negative this thing inside is, when I square it, it becomes positive. So yeah, this one is actually always true. Cool. Part 2. If ax is greater than b, then x is greater than b every way. This is a classic little trick with inequalities. So I think a lot of the time you might be led to believe that that's true, right? It kind of makes sense. Like, what have they done there? They've divided both sides by a. Makes sense. However, if I multiply or divide an inequality by a negative number, I have to flip the sign. That's that one thing that we need to remember about with inequalities. So basically, the thing that I'm dividing by is a, isn't it? So if a was negative, then ax being greater than b would actually imply, so I'd divide both sides by a, so I'd get x and then b over a, But because a is negative, I'm divided by a negative number, I need to flip the inequality. So in that case, it wouldn't be true, would it? But if a is positive, then it is true. So I reckon this one is that it's sometimes true. Maybe if you want to be super sure here, you would also, because I've obviously shown cases in which it's not true. I've not actually yet shown cases in which it is true. So maybe just to be super certain I'm getting the marks here, I would then say, well, actually, if a is greater than 0, then yeah, ax being greater than b would imply that x is greater than b over a. So now I've shown cases where it isn't true and where it is true. So I've shown that it's sometimes true. Cool. The difference between consecutive square numbers is odd. They're making you graft in this. This might take a while. So really, we're just going to need to do a proof here. Again, start subbing in square, consecutive square numbers. You'll be here for an infinite amount of time. Don't do that. So let's have a think about how to do this algebraically. So how can we represent a square number? N squared, right? Where n is an integer. Now, consecutive square numbers. So consecutive is, they're next to each other. So instead of me just saying kind of m squared, that would just represent any other square number. But I actually want the next square number, don't I? So the next square number is going to be n plus 1 squared, right? So as an example of that could be 3 squared and then 4 squared. So n squared, n plus 1 squared. And I want the difference between these two things. So the difference is, 1 minus the other. So this one's going to be bigger. So I'm just going to do this one minus that. See if this thing's odd. So I'm going to multiply out this bracket to get n squared plus 2n plus 1. And then I'm going to take away this n squared. So the answer here is 2n plus 1. So is this always odd? Well, let's look at this bit. 2n. That's always even, isn't it? Because it's n, which is an integer, a whole number, multiplied by 2. Anything multiplied by 2 is even. An integer multiplied by 2. And then I add 1 to it. So I get an even number, add 1 as an odd number. So yeah, this thing is actually always odd. Always odd. So basically, yeah, this thing is always true. So a bit of a proofy question there. Filling in a table. I didn't think it'd take that long, but there we go. Alright, question 7 says use the binomial expansion in ascending powers of x to show that square root of 4 minus x equals a load of stuff up to the x squared coefficient. K is a rational constant to be found, so it might be a fraction here. Right, so bit of confusion on the binomial expansion. I get a lot of questions on this, so let's clear it up. So this is what we have in the formula booklet for binomial expansions. And you can see that there's 2 of them. So you might be confused as to which one to use, right? So what's the difference? I mean, okay, well, a couple of differences. We can see that this is a plus b to the n. So, these, they can be any numbers, right? Don't have to be 1. This one is a 1 plus x to the n, so the first number has to be a 1. It's not valid for 2 plus x to the n or 3 plus x to the n. One more really important thing, which is the most important thing, is this is only valid for when n is a natural number. What do we mean by natural number? Ones that you might feel natural to come up in life, right? I have 1 apple, I have 2 apples, I have 3 apples. Positive integers, essentially. Back in the day, people only really thought that natural numbers exist, right? So this one on the bottom, any real value of n. So if I have a binomial expansion where the power is not a nice positive integer, but instead it's, I don't know, minus 6, 1/2, e, you're not going to get e, then we have to use this bottom one. So let's have a look at what we currently have. We have the square root of 4 minus x. Well, what is this as a power? It's a half, isn't it? Okay. Well, can we use either at this point? No, we can't use any because, okay, we know that we're going to have to be on the bottom one because a half is not a natural number, but I've not got 1 here yet, have I? I've got a 4. So what I instead need to do is I need to take this 4 out. Now, mistake alert, yeah? I can't just do that. I can't just say 4 and then what? What would that be? That would be 1 minus x over 4 to the half. I've taken 4 out, right? Not quite. And the reason is because this 4 is still in this power of a half, isn't it? So let me do this longhand for you, right? What I'm going to do, these brackets are still here. So, you know, brackets for the half are still here. And now within these, I'm going to take a 4 out of this 4 minus x. So I'm going to say 4 times 1 minus x over 4. So now look, I've got everything to the half here. So this is now going to be 4 to the half multiplied by 1 minus x over 4 to the half. That's what you need to be careful of here. So obviously 4 to the half is 2, and then I got 1 minus x over 4 to the half. Okay, so are we now in the position where we can use this? We are. And you might be thinking, wait a minute, that's not an x. But it is if you just considered this to be a new variable, right? So like I could literally say, why don't I define y as minus x over 4? Then I would have 1 plus y to the n, wouldn't I? So, you know, we are allowed to, you need to make sure there's a 1 there, but don't be put off if it's not just plus x. It could be 2x, it could be minus x over 4, because variables are variables, aren't they? We can redefine them. Okay, so that's the reason I can use this. So essentially my x in this is just going to be a minus x over 4. And I basically just sub it in at this point. So the 2 is going to be chilling on the outside, so we'll keep that there. I'm going to go over here because I'm probably going to need a bit of space. So 2 times whatever this is. Now, you can see that in the question, they only want the first 3 terms. So I'm going to work those out now. So the first term is 1, easy enough, plus n. What's my value of n here? It's 1/2. Multiplied by x. My value of x is, remember, this minus x over 4. So just one more term at this point. I have plus n, so 1/2. N minus 1, well, that would be a half minus 1, which is minus a half. Divided by 1 multiplied by 2 times by x, which we know to be minus x over 4, all squared. And then we do have a plus dot dot dot, but as we say, we don't care about those terms. So just work out what this is essentially, and hopefully you should be good. So let's keep this 2 out here, and let's see what we can do. So a half times by minus x over 4 is going to be minus x over 8. Oh, I've still got the 1 here. Right. You can go to your calculator here. I don't mind. So let's work it out. So I'm going to have a load of fractions. I'm going to have a half multiplied by minus a half divided by 1 times 2, or 2. And then multiplied by, you know what? I want to write this out for you so you can really see. So just this fraction here is going to be minus an 8th. So it's going to be minus an 8th. And then what is minus x over 4 squared? Well, I need to square everything. So I'll square the minus sign, it goes to positive. Square the x, so it goes to x squared. Square the 4, so it goes to 16. And then plus dot dot dot, obviously. Okay, so now we're kind of in a good spot. So we're going to have 2 multiplied by 1 minus x over 8. And then minus, what's 8 times 16? It's going to be 128. So we have minus x squared over 128. Now I can multiply this 2 out. So I'm going to get 2 minus x over 4 minus x squared over 64 plus whatever. So I think that's it for part A. K is a rational constant to be found. So that is going to be this thing here. So K is going to equal minus 1 over 64, I believe. And then the first 2 terms, yeah, are 2 and then minus a quarter x. Cool, so that's a bit of a confirmation that I'm on the right lines here. The student attempts to substitute x equals 1 into both sides of this equation to find an approximate value for the square root of 3, which would kind of make sense, right? Because we know that the square root of 4 minus x is equal to all of that. So if I stick x equals 1 in, on the left-hand side, I'd have the square root of 4 minus 1, which is the square root of 3. Is this valid? How do we know if it's valid? Let me take you back up to the formula booklet. Look at this. What do we have here? It basically says, look, this is only valid if n is a real number and if the modulus of x is less than 1, okay? So, but remember, in our case, our x is actually minus x over 4, okay? So our expansion is valid for the modulus of minus x over 4 being less than 1. So, well, minus sine modulus, that's just going to be that. I can multiply both sides by 4 to get the modulus of x has to be less than 4. In other words, I'm allowed to use this expansion if the value of x I want to eventually sub into it, the modulus of it is less than 4. Is the modulus of 1 less than 4? Yeah, it is, isn't it? So yeah, it's valid, basically. We are completely allowed to do that. Question 8, what is that? Okay, it's a rectangle. A lies on the y-axis, B and D lie on the x-axis. Okay, the straight line through the points A and B is equation that. Show that the straight line through the points A and D is equation that. Okay, let's get the diagram up. Let's get a bit of an idea about what's kicking off here. Looks like we have the equation of that, and we want the equation of that. So what two things do we need to get the equation of a line? We need a gradient, and we need a point x1, y1. If we have those two things, we can sub them in to y minus y1 equals m x minus x1. So we just got to try and get those two things. How can we do it? So I can think about how to get the gradient here, because if this is a rectangle, this is a right angle. So the lines are perpendicular. So I know how to get perpendicular gradients. So what I'm going to do is I'm going to get the gradient of AB here. So let's rearrange AB into the form y equals mx plus c so we can just pop that gradient off. So I'm going to take the 2x over to the other side to get 5y equals minus 2x plus 10. I'm going to divide by 5 to get y equals minus 2 over 5x plus 2. So now the gradient of this thing here is minus 2 over 5. And now to get a perpendicular gradient, what I need to do is I need to do minus 1 divided by that. In other words, flip the fraction and change the sign. So in this case, sign's going to go positive, fraction's going to flip to get 5 over 2. Now I just need a point. So what I'm noticing is they both go through point A, don't they? So because I have the equation of AB, I can basically find out the point A, and then I know that it goes through AD as well. So the point A is where they both hit the y-axis. In other words, x is going to be 0 at this point, isn't it? So if I put x equals 0 into the equation of AB, then I can say that, well, that point is actually going to go through this as well. So what I'm going to do is I'm going to put it into this equation here. Why not? Yeah, let's put it into this equation. So x equals 0 would imply that 5y equals 10, or that y is equal to 2. So I know that they both hit the y-axis at 0, 2. Fantastic. So I've now got enough information to go straight to here now. So I'm going to get y minus, and then y1 is going to be 2, equals, I wrote y1 when I meant to write 2, equals m, which is going to be 5 over 2, multiplied by x minus x1, which is 0. Cool, okay, that's the equation. But let's just quickly look and see if they want a specific form. So it looks like they have no fractions in their answer. So what I like to do, I usually tend to get fractions and gradients, right? They just naturally happen. So what I like to do is just multiply up by this denominator. So I'm going to multiply everything by 2 here to get 2y minus 4 equals. I'm just going to be left with 5 here and then x inside the bracket. Cool. And then it looks like they want the y's and the x's on the same side. So the answer is going to be 2y minus the 5x, and then I'm going to add that 4 to the other side. And that looks to be good. Okay, find the area of the rectangle ABCD. Okay, so obviously area of a rectangle is width times height. If we could just find out the length of AD and the length of AB, then I can just multiply them together. Let's start with AD. We know this point A, okay? If we just knew this point D, then what we could do is we could use Pythagoras to work out the length of that line AD. So I think we can work out the coordinates of D because that is where the line AD is the x-axis. So if I set y equals 0, I'm going to get that x coordinate. So let's do that. So the equation of AD is this here, isn't it? So when y equals 0 this time, I'm going to get minus 5x equals 4. This is going to let me know that x is equal to minus 4/5. So straight away, I know the coordinates of this point. It's going to be minus 4/5, 0. Okay, so I've got minus 4/5, 0, and 0, 2. Basically, if I was to draw a right angle triangle here, I can use Pythagoras to get the length of AD. So let's do that down here. I've got minus 4/5 and 2. It's basically the difference between the x-coordinates squared plus the y-coordinates squared. So what we're going to do is we're going to have, look, the x-coordinates are minus 4/5 and 0, so the difference is 4/5. So it's going to be 4/5 squared plus, and then the y-coordinates are 0 and 2, so plus 2 squared. Straight to your calculator, that's going to get you the following. All squared plus 2 squared. Something pretty grim looking. 2 times the square root of 29/5. Looks, I don't know, it looks fine, I suppose. Not the greatest thing, but it doesn't matter. Okay, so we know the length of AD. If we just get the length of AB, we're laughing. But we can do the same thing. We know it goes through A, and then we know it also goes through the point where the AB line hits 0. So how do we do that? We're going to set y equals 0 in the equation of AB. So the equation of AB, I mean, we're just given in the question. So we're going blue here. So y equals 0 now in this one is going to imply what? It's going to imply, so 5y plus 2x equals 10. So 0 plus 2x equals 10. That's going to get me x equals 5. So what do we know? We know that this point B is the point 5, 0. Okay, so we have 0, 2, and 5, 0. Again, we're going to do Pythagoras. I know there's quite a lot going on here, but it's similar stuff, so we're repeating ourselves a lot. So we're going to get what? We're going to get 5 squared plus 2 squared. Differences in the x squared, differences in the y squared. This is going to be the square root of 25 plus 4, which is 29. Whew. So the area, finally, I can see it being a bit nicer now. Because it's going to be this 2 root 29/5 multiplied by this root 29. So we can see that these square root of 29s kind of go in pretty nicely, don't they? So I'm going to get the 2/5, and then root 29 times root 29 is just 29, isn't it? So that's going to be my answer here, which is going to be 2/5 times 29. So as a fraction, 58/5. And I think keeping it as a fraction is the best thing to do here. It's nice and exact. No rounding or decimals needed. Question 9. I'm hoping this will be a bit quicker. I was losing my momentum a bit on question 8. So given that A is a constant, alright, okay. So they like doing this. I think they did this in paper 1. It's basically just give you an integral and then it's equal to something. So you just solve the integral, don't you? And then stick it equal to that and you'll have something. So let's basically integrate this thing. 3 root x. Now, it's better to write things like square roots in terms of the powers. So the square root is a power of a half. Because then I can kind of use that law, you know, add 1 to the power, all of that stuff. Plus a dx. So what's this going to be equal to? So it's a definite integral, so I'm going to want some square brackets here. Okay, so I'm going to add 1 to the power. So a half add 1 is 3/2. I'm going to divide by the new power. So I'm going to divide by 3/2, which is the same as multiplying by 2/3. And I need to remember that I've still got a 3 there, so there's going to be a times 3. That's the first term, and then a is just a constant. So if I integrate a constant, it's just going to be that constant multiplied by x. So that's going to be plus ax. And then I put my limits in. Okay, so all I'm going to have is one bracket minus another bracket. This bracket is just going to be 4 subbed in. Now quickly, 2/3 times 3, well the 3's are going to cancel, aren't they? So I actually just have 2x to the 3/2 here, which is nice. So I have 2 times 4 to the 3/2 plus 4a. And then minus, I have 2 times 1 to the 3/2, which is just going to be 2. And then plus ax, so a times 1, so plus a. Okay, so what's this going to be? Now 4 to the 3/2 I mean, you can just put this in your calculator, but basically what you would do is you would do 4 to the half first. So that is 2. And then that would be 2 cubed. So this is actually going to be 8 here. And then plus 4a minus 2 minus a. So 2 times 8 is 16 minus the 2. And then plus 4a minus a is plus 3a. So what do I have? I have 14 plus 3a. And now I am told that that thing is equal to 2a squared. So it looks like I have a quadratic equation here, doesn't it? I'm going to have 2a squared minus 3a minus 14 is equal to 0. And I just solve it. So you do what you want. You could try and be clever. You could factorize it. Mental energy that I don't have right now. So what I'm going to do is I'm going to go to my calculator, menu, equation func. It's a polynomial. It's degree 2. And I'm just going to put my coefficients in. So 2 minus 3 minus 14. And then press equals, and it's just giving me solutions. Oh, technology. 7 over 2 and minus 2. And then they are the 2 possible values for A. Alright, in a geometric series, the common ratio is R, and the sum to n terms is Sn. We know that. Given that, okay, so S infinity, sum to infinity, is equal to 8 over 7 multiplied by the sum of the first 6 terms. Show that R is that. So it's just that they're giving us an equation, aren't they? Luckily for you, S infinity and Sn are in your formula booklet. So S infinity is A over 1 minus R. Sn is, what is it again? A times 1 minus R to the n over 1 minus R. They're in your formula booklet, so I don't even need to talk to you about these. Essentially, stick them in, solve it. Now, A is the first term. So S infinity, A over 1 minus R, is equal to 8 over 7 multiplied by S6. Okay, so A times 1 minus R, and then n being 6 in this case, over 1 minus R. Now we've got an equation, we just solve it, so there's nothing too mad kicking off here, just need to be careful. So first thing I'm noticing is look at these A's, they can cancel. Look at these 1 minus R's, they can cancel, so it's actually getting quite easy now. I'm left with 1 on the left hand side, aren't I? So I'm going to have 1 equals 8 over 7 multiplied by 1 minus R to the 6. Already a lot simpler. I'm going to multiply by 7, divide by 8 to get 8 over 7. Ooh, not quite, to get 7 over 8. We all make mistakes, we just got to find them. So equals 1 minus R to the 6, because I'd just be left with 1 there now. And just solve for R, right? So I'm going to add R to the 6 to both sides. And then I'm going to take 7 over 8 from both sides. So 1 minus 7 over 8. So if I have, that's basically 1 minus 7 over 8. I've just got one lot of 8s left. So now I think I'm good. I just say that R is going to be 1 over 8 to the power of 1 over 6. Now, basically, we do need a plus minus here. And that is because 6 is even. So for for a square root, we need a plus minus. We don't for a cube. We do for a power of 4, etc. Okay, let's have a look at what they want. Obviously, this is not their answer. So can we do anything cheeky here? Let's have a think. 1 over 6. Now, there's something I'm noticing about this 8 here. And that is that, you know what? Before I even get onto that, I want to be less confusing about this fraction. So let's do this longhand. This is going to be 1 to the 1 over 6 divided by 8 to the 1 over 6. 1 to the 1 over 6 is just 1. So that's why I wanted to do this, just to kind of get it a bit simpler for you. Okay, 8 to the 1 over 6. Now, to be honest, at this point, you could just put 8 to the 1 over 6 into your calculator and see what you get. I'm going to be a bit clever about it, though, because I want this to be instructive. So I know that 8 is a cubed number. So if I have 8 to the 3rd, that would actually be 2, because 8 to the 3rd would be the cube root of 8, which is 2. So I've not quite got that, but what I could do is something like this. I could say, well, 8 to the 1 over 6 is 8 to the 3rd all to the half. So at this point, I can say, well, wait a minute. 8 to the 3rd is 2 So it's just 1 over 2 to the half. And then, well, a half is just the same as a square root, isn't it? So this is actually going to be plus minus 1 over the square root of 2. Question 11. Figure 2 shows a sketch of a part of the graph y equals f of x where we've got some modulus and some other stuff kicking off. State the range of f. Okay, let's get this graph up here so we can kind of talk about it. I mean, we can clearly see, right, it goes down to whatever this point happens to be, and then it just goes up, and it keeps going up. And if you look at the domain, it's basically x is greater than or equal to 0. In other words, this goes up forever. So this isn't going to have an upper limit here. It's going to go up to infinity. So basically, it's just going to be greater than or equal to whatever this value is here, isn't it? So what is this minimum point then? Let's have a look at the different components of f of x. So we've got 2 times the modulus of 3 minus x, and then we've got plus 5. Okay, so this thing is just always a plus 5. It's not variable at all. And then this thing, well, it's always going to be positive, isn't it? Because it's a modulus. So, you know, no matter how negative this is, the modulus sign is obviously just going to make it positive. So what is the smallest value that this thing can be here? Well, it's going to be 0, isn't it? A modulus can be 0, but it can never be negative. So obviously 2 times by the 0 is still going to be 0. So this thing here is always greater than or equal to 0. And then this thing is obviously just plus 5. So the smallest value that this whole thing can be is just going to be 5, isn't it? It's when this is 0, so the whole thing is going to be 5. So the range is just going to be y is greater than or equal to 5. Solve the equation f of x equals a half x plus 30. Okay, so I suppose the equation that we're trying to solve is the following. 2 multiplied by the modulus of 3 minus x plus 5 is equal to a half x plus 30. Now, I always like to kind of have a bit of a step back here. So, I mean, there's a few ways of solving just kind of standard modulus equations. A way that I like to do it is I separately solve the kind of positive version and the negative version of the modulus. In other words, there's kind of 2 situations that can arise here. There is basically the fact that this thing inside the modulus was positive anyway, so the modulus signs actually aren't doing anything. So it's the same as solving the equation 2 times 3 minus x plus 5 equals a half x plus 30. So that might be one kind of equation to solve. And then the other one is that this 3 minus x was negative, but then the modulus made it positive. In other words, the modulus flipped the sign of everything inside the 3 minus x. So that would correspond to the equation 2, and then flipping the sign of the 3 minus x would be multiplying by x minus 3, and then plus 5 equals a half x plus 30. So you could just kind of jump into that, but I think you need to be a bit more careful. And that is where graphs come in a lot of the time. Because it might just be that for my f of x, only one of these is valid. If I just went willy-nilly started solving these 2, I'd get 2 solutions. But then one of them actually might not be valid. Like, look at what we have for x here. X, you know, this graph f of x is only defined for when x is greater than or equal to 0. So if we were to give just a super rough sketch, of when this graph intersects the graph of y equals a half x plus 30, then we might start getting a bit of an idea about what's kicking off here. So a half x plus 30, well, it's going to hit at y equals 30, so higher than this, isn't it? So, I mean, it'd probably be right up here, but for the purposes of this sketch, let's put it here. And then a half x, so a pretty kind of shallow gradient. So basically, you know, this line is going to go down here and then up here, basically, you know, forever. So we can actually see that it's going to hit, because this, we know that this actually goes on forever too. So you know, there's going to be some point up here where they're going to hit. But only one point. They're not going to hit over there, because f of x isn't defined for negative x values. So if I was to jump in and solve both of these equations, it wouldn't work. I actually only need to solve one of them. So the question is, which is the equation that corresponds to where they hit? Let's have a think about it. So it's going to be, imagine the graph without the modulus. It's going to be, 3 minus x. So the x, it's going to be y equals, and then it's going to have a negative gradient, isn't it? So this chunk of the graph is the chunk for which the modulus sign isn't doing anything. In other words, it would just be 2 multiplied by 3 minus x. And then when it starts flipping up, that is when the modulus sign is actually flipping the sign of that 3 minus x. It's saying, well, 3 minus x was negative, so I'm changing it to an x minus 3, so it becomes positive. And that is the section of the graph that is going to hit this red line here. So what I'm going to do is I am going to solve equation 2, because that is the equation that corresponds to that bit going up to infinity. So I just solve equation 2, and that's going to be the only value of x here. And that's why this is a hard question. It's because you really need to think about, actually, what are the solutions of x that will be valid here. So quickly, I think you know how to do this, but I'm going to multiply this out quickly. 2x minus 6. I'm going to add a 5, and that's going to be equal to a half x plus 30. Okay, let's take this half x over to the left-hand side. So 2x minus a half x. I'm going to have 1.5, or 3 over 2x left. Minus 6 plus 5 is going to be minus 1, I believe. Yes. So I'm going to get minus 1, and then I'm going to add it to this right-hand side. So I'm going to get 3 over 2x equals 31. Okay, so x is just going to be 2 over 3 times by 31. Let's get this as a nice little fraction. So that is going to be 62 over 3. Cool, okay. Given the equation f of x equals k, where k is a constant, has 2 distinct roots. State the set of possible values for k. Okay, 2 distinct roots, that's important. And again, graphs. I think with modulus equations, graphs just help so much with the understanding of what's going on here. So, okay, so f of x equals k. So in other words, if I want to kind of solve this equation, it will correspond to where the graphs of f of x, y equals f of x, and y equals k intersect. So, y equals k is going to be some horizontal line, and then depending on what the value of k is. So imagine that this horizontal line is here. So k would be a number down here. Well then, they're not going to intersect. There's going to be no solutions, isn't there? If k was corresponding to just this minimum point here, which we actually know to be 5, don't we? Then there would be one distinct solution. And then we have this sweet spot, don't we? All around here, there's 2 distinct solutions, right? It's the one on the left and the one on the right. But then, after this point here, there's one distinct solution again. So basically, what we want is this sweet spot, don't we? We want the range of values for k here. So we actually know the bottom one. It's 5, isn't it? Do we know the top one? Well, I don't think we do right now, but can we work it out? I think we can. So this value here is going to be when x equals 0 in this graph of f of x, isn't it? So let's work that out quickly. So for part C, I'm going to say that f of 0 is equal to 2 multiplied by the modulus of 3 minus 0 plus 5. So this is going to be 2 multiplied by 3 plus 5, which is 6 plus 5, which is 11. Okay, so this is the point 11. So it's going to be between 5 and 11. I just want us to be really careful on if it's going to be greater than or equal to, just greater than, all of that stuff. Okay, so when it's at 11, we are going to get 2 distinct hits, aren't we? Because it's going to intersect here and here. But when it's equal to 5, there's actually only going to be 1 intersection point. So I think for it to have 2 distinct roots, it's going to be less than or equal to 11, but it has to be strictly greater than 5. So I think that the answer to this question is k is less than or equal to 11, but strictly greater than 5. Question 12. Solve for x between minus 180 and 180. Degrees, by the way, so make sure that this old chestnut is in degrees. Do that before every trig question. Make sure it's in the right unit. The equation, that thing there. Okay, this is a quadratic trig equation. It's got kind of sine squared, sine, cos squared, stuff like that. And I really want you to be familiar with this type of equation. There is a pivotal identity that we use, and it tends to be cos squared plus sine squared equals 1. basically that means that if I have a sine squared, I can swap it for a cos squared, and if I have a cos squared, I can swap it for a sine squared, right? So not swapping it as in like a function of sine squared, right? So the question is, which one do I do, right? I've got sine squared, but I've also got cos squared. So I want to let this term in the middle decide, this sine x. Think about it. I can change a sine squared into a function of cos squared and vice versa, but the sine is just going to stay a sine. I can't change that sine into a cos, right? So what I'm going to need to do is make everything in terms of sine here, just because of that sine term in the middle. So what I'm going to do is I'm going to write the left-hand side out, and I am going to swap the cos squared on the right-hand side with a 1 minus sine squared. Cos squared plus sine squared equals 1, therefore cos squared is 1 minus sine squared. Let's multiply this out and clean up, and we're going to see what we're left with. I'm going to add 9 sine squared to both sides to get 3 plus 9, which is 12 lots of sine squared. Just got sine x still here, and then I've got 8 minus 9, so that's going to be minus 1. Okay, now this is actually a quadratic equation, but in sine x. Now if you don't believe me, why don't you just let y equal sine x? What would that then lead to? That would lead to 12y squared plus y minus 1 equals 0. Now again, you can use a calculator and stuff. I think this is factorizable here, so let's do it. We know that these numbers are going to be 1 and minus 1, because that's the only way to get a product of two numbers to be minus 1. Okay, now I think that if I have a 3 and a 4, this is going to work, because y is obviously that, like one lot of y. That's going to be 4 minus 3. So if I get a positive 4 here, okay, so if I have 4y here, when I multiply that by the one that's going to be positive, and if I have 3y here, when I multiply that by the minus 1, it's going to be negative. Let's have a think. So 3y times 4y is 12y squared, minus 3y plus 4y is going to be plus y, and then 1 times minus 1 is minus 1. Fantastic. So this gives me two values of y, doesn't it? It gives me y equals minus a third and y equals a quarter. In other words, sine x equals minus a third or a quarter. You don't have to do the y, you can literally just write sine x instead. I just did it to really kind of show you that this can be a quadratic. Okay, so in this case, I've done, the meat of this now, but I do still need to get all the solutions. So I'm going to draw the sine graph. I'm not a fan of the cast diagrams. If you are, that's completely fine. I don't know. I just don't seem to get on with them. So if I have the sine between minus 180 and 180, it'll look something. See if I butcher this like I usually do with graphs. All right, that could have been worse. I'm happy with that. So this is 180 and this is minus 180. So in other words, my solutions are going to correspond to where it intersects y equals a quarter and it intersects y equals minus a third. So it looks like in our case we're going to have 1, 2, 3, 4 solutions. It's always, I do that before I even touch the calculator. I'm not getting any values. Some people jump into just getting the arc sine straight away. I like to just visualize it and say, okay, I know I'm looking for 4 solutions, so I can check at the end really if that's how many I've got. Okay, at this point I can go into my calculator to get the first ones. Let's do the quarter one first. I'm going to do the inverse sine of a quarter to get the following. Inverse sine of 1 over 4 gets me 14.4775, a few more. So that's going to be this, isn't it? The 14 ... So I'm going to use the symmetries of the graph now. So if this distance here is 14, is that, then by the symmetries of the graph, so is this distance here. In other words, if I was to do 180 minus that 14, I'd get my other solution. So if I just do 180 minus ants in my calculator, I'm going to get 165.52248 ... So that's going to be these two. Now what I need to do is get this, which is going to be the inverse sine of minus a third, which is going to be minus 19.47122 ... I'm going to round these, to more decimal places later. It's just nicer to have it first, because then later on, we might use them in other calculations, all of that stuff. So, and then similar kind of thing, right? If this distance here is that 19 value, then this distance here is going to be that kind of 19 value again. So if I just do minus 180 minus answer, that is going to get me my last solution, which is going to be minus 160.5287 ... Okay, now it says, okay, 2 decimal places, so I'm now going to round them to 2 decimal places. So I'm going to get 14.48, 165.52, minus 19.47, and minus 160.53. Fantastic. Bit of a big old question there. Now, part B, it says, hence find the smallest positive solution of the equation. Okay, that equation looks horrendous. It looks grim. But it's not actually that grim. Why? Because the only difference between that disgusting piece of maths and the equation in part A is that the x has been swapped for a 2 theta minus 30, right? But wait a minute, we've already solved the equation in part A for x, right? So we know all of the x values that solve this equation. So if the only thing that's happened is I've swapped an x with a 2 theta minus 30, then surely the solutions for 2 theta minus 30 are also just going to be all of these, right? And yeah, they are. So that's not that bad, isn't it? We've already kind of solved the equation, as it were. We need to be careful, though. We now need the smallest positive solution of this equation. The smallest positive solution for theta. So a mistake would be to say, okay, well, clearly the smallest positive solution here is this 14, so I'm then going to solve 2 theta minus 30 equals 14.48. That wouldn't be correct, and the reason is because I want the smallest positive solution for theta. Have a look at this minus 19. If I was to add 30 to that, I would get 2 theta equals, and then some positive number, because 30 is bigger than 19. So that would actually get me a positive solution, and it would definitely be much smaller than the one corresponding to this. So what I actually want to solve is 2 theta minus 30 equals this thing here. Now, what I want to do is I'm actually going to... Okay, I can write this, but when I finally put it into my calculator, I want to use this longer value just to avoid rounding errors. Remember, I always say this in mechanics and everything. It's basically, if you're using a solution to a past part of the question, and don't use the rounded solution. I know for the answer of part A we wanted them rounded, but if I want to use it in another calculation, I want to, have as much accuracy as I possibly can, so it doesn't, introduce any rounding errors later down the line. So I'll write this out for now, but I'm going to use kind of this in my calculator. So I would basically be solving the equation this. Or 1, 2, 2. I'll just write that down so you know what I'm doing here. Okay, so solve it, right? So theta is going to be 30 minus that thing, all over 2. Now I'm going to put this into my calculator. So I'm going to get 30 minus, and then just give me a load of accuracy. So 19.47122 all over 2, which is going to be 5.26439. And then to 2 decimal places, I'm going to get theta equals 5.26 degrees. 13. Here we go. So part A says express 10 cos theta minus 3 sine theta. So let's get that down. 10 cos theta minus 3 sine theta in the form r cos of theta plus alpha. Okay, so from the formula booklet, what is cos of theta plus alpha? It's going to be cos alpha cos theta minus sine alpha sine theta. So if we want this in the form r cos of all of that, well then r multiplied by cos of theta plus alpha is going to be r cos alpha cos theta minus r sine alpha sine theta. So why have I done this? And why have I written it in this specific order? Because look at this. I have the cos theta here, so then that means that this r cos alpha must be equal to 10. And then minus some lot of sine alpha. So that r sine alpha must be equal to 3. So what I've actually got here is 2 simultaneous equations. So I'm not going to go through absolutely every step on how to solve these, but I will do it relatively quickly. So the first thing I'm going to do is I'm going to do equation 1 divided by equation 2, and that is going to get me r sine alpha over r cos alpha is equal to 3 over 10. R's cancel, sine over cos is tan, so I get tan alpha equals 3 over 10, which gets me alpha straight away. Just going quick here. So, okay. I can get my alpha, might as well do it now. I am in degrees, so let's just do the inverse tan of 3 over 10, or 0.3, which is going to get me 16.699, or 16.7. to 1 decimal place. Okay, and then basically the identity we're going to use for getting the r is we're going to square both sides. I'm going to go through this pretty quickly, but we're going to square both sides and then add them together. So essentially you would get r squared cos squared alpha plus r squared sine squared alpha is equal to 10 squared plus 3 squared. Why have we done this? Because if we take an r squared out, we would get r squared times cos squared plus sine squared. I know I'm wishing this because basically once you learn it, you don't have to go through it really slowly each time. You know, they'd be happy with you just kind of going straight to the tan or straight to the kind of getting the r squared. You don't need to do this working out every time. But basically, yeah, that's going to be 10 squared plus 3 squared, which is 109. Cos squared plus sine squared is 1, isn't it? So that just goes to 1. So r is going to be the square root of 109. So that happens every time. So you just kind of learn it, basically. So yeah, in other words, what we now have is the square root of 109 multiplied by cos of theta plus 16.7. Cool. Okay, so part B. The height above the ground, h meters, of a passenger on a Ferris wheel t minutes after the wheel starts turning is modeled by the equation, that thing there. Okay, so looking at kind of the relationship to part A, it does look like we kind of have almost got 10 cos theta minus 3 sine theta. We've got 10 cos of something, and well, we've got minus 10 cos of something plus 3 sine of something else. So if that AET was kind of theta, and then if it was just minus all of that, we would. So there's definitely a relation to part A here. Always be thinking about that. Given that the initial height of the passenger above the ground is 1 meter, find a complete equation. Well, what does complete equation mean? The only reason this equation isn't complete is because we've not got the value of A. So we're just going to use this piece of information to get the value of A. Everyone's happy. So, initial height. So initial, t is going to be 0, and then we're told it's 1. So if I sub h equals 1 and t equals 0 into this, I think I'll be laughing. So I'm going to get A minus 10 cos of 0 plus 3 sine of 0. Okay, sine of 0 is 0, cos of 0 is 1. So I'm going to get A minus 10 here. So A is going to be 11. Fantastic. Hence, find the maximum height of the passenger above ground. Okay, so this is where part A is going to come in. The reason we like to express things like we do in part A is because when I have multiple trig functions, right, like cos and a sine, I know that both individually they go between 1 and minus 1, but when I'm adding them together, it's hard for me to know kind of, okay, well, cos is going to have a max at minus 1, but what's the sine going to be doing then? And what's the, how do I balance them out fully so that just together we have a maximum? Well, the answer is it's difficult. So it's actually better to write it in another form. If you instead have it in this form, it's a lot easier because we just have this cos here. We say, okay, well, the cos is between 1 and minus 1. It's going to be max when cos is 1. It doesn't matter about what's inside here as well. That's a lot nicer. So let's get that kind of in this form. So what we're going to do is we're going to rewrite h. So h is 11. And then what I'm going to do is I'm going to take a minus sign outside here. And then inside this bracket, I'm going to have 10 cos of ATT minus 3 sine of ATT. This is useful because if we look at what we have inside this bracket, isn't that exactly what we had in part A, but instead of theta we have ATT? Yes, so what I can do is I can say that this is the same as 11 minus this thing here. The square root of 109 times cos, and then instead of theta we have ATT, plus 16.7 degrees. Fantastic. So now this is a lot easier to maximize and minimize, stuff like that. So it says the maximum height. So this is super easy now. I don't care about how confusing this thing inside the cos is, because all I know that the cos, this is between 1 and minus 1, isn't it? So how am I going to maximize h here? Well, because I'm minusing this, I want to make this kind of as negative as possible so it'd actually turn into a positive. It'd maximize it, wouldn't it? So the maximum value of h is going to occur when this thing here is equal to minus 1. So the h max is going to be 11 minus the square root of 109 multiplied by minus 1. So that's going to be 11 plus the square root of 109. Cool, okay. Find the time taken to the nearest second for the passenger to reach the maximum height on the second cycle. Right then. So let's probably going to have to start using the brains, unfortunately. Might be a bit of thinking involved in this one. Right, so second cycle. Now, it's basically to do with solving for t, right? So the question is, let me just think of a cos graph for now. So thinking of a cos graph, right? Just going to go like this. I'm going to go like this. I'm going to go like this. That's 2 cycles of a cos graph, okay? Now, the maximum height of h is going to correspond to when this cos is equal to minus 1, isn't it? So we kind of know what happens. It's going to reach its maximum height here when cos is equal to minus 1. So that's the first time it reaches it, but we care about the second time it reaches it, don't we? So what we're going to do is we're going to say, okay, well, our solution is going to correspond to then this kind of second solution when it's minus 1, essentially. Okay, so essentially we kind of want to solve this. We want to solve cos of ATT plus 16.7 is equal to minus 1, and we want this second solution here. So what I'm going to do, basically this here, let's just get, this is kind of stuff you should know, but essentially, so cos has a period of 360, so this is going to be 180, so what's this going to be? It's going to be 540, 360 plus another 180, okay, and that is what we care about. So in other words, this thing here, ATT plus 16.7 is going to equal 540, and now I can solve for t. So take away 16.7 and divide by the AT. Now I'm just going to check. Okay, so I've got an answer on my calculator, which is that 16.7, but it's less rounded, it's more accurate. So I am going to use that in my calculation. So what I'm going to do is I'm going to write 540 minus ants, and then all of that is going to be divided by 80. Just try and minimize your rounding errors. So in this case, I have t equals 6.541 ... and then it wants, what does it want? It wants the nearest second. Okay, and I believe this t is measured in minutes, is it not? Let's see, yeah, t minutes. So how am I going to do this? So, okay, this 6 corresponds to 6 seconds. 6 minutes, which is 360 seconds. This 5.541, how many seconds is that going to correspond to? Well, if I multiply that by 60, I'm going to get that, aren't I? So I've actually got, again, you know, a more accurate version here. If I do ants minus 6, that's just going to get me the kind of the decimal bit of this. Now I'm going to multiply this answer by 60 to get how many seconds. So this tells me that I get kind of 32.47 seconds. So this is going to be 6 minutes and 32 seconds. Cool. So last part says, how would you adapt? Well, it's decided to increase profits, the speed of the wheel is to be increased. That sounds like a disaster waiting to happen, doesn't it? How would you adapt the equation in the model to reflect this increase in speed? Look at this h here. Look at the graph of this h. We've got, you know, it's going, I know there's, I'm not going to, you know, it's going up and down and up and down and stuff like that. And obviously we have time here. So, you know, wheel spinning, going up, down, etc. What they want is they want it to go, you know, up, down, up, down, up, down, quicker, don't they? In other words, they want to kind of take this graph and they want to squish it, don't they? You know, if I take loads of these black ones and then just kind of push them all together, I'm going to get this red. I'm completing more cycles in that same amount of time. So thinking about kind of transformations, what would that correspond to? Well, you know, the kind of oscillating nature of this equation is from the trig, isn't it? It's from the cos and the sine, okay? So how would I kind of transform the cos and the sine so that it squishes in? Think of our graph transformations. Essentially, if I have f of, you know, ax, this is a stretch in the x-axis with scale factor 1 over a, okay? So basically, if I increase this value of a, it's going to be squashing the graph in horizontally more. So the thing that corresponds to that is that ATT inside the cos and the sine, isn't it? Because ATT is going to be kind of going like that, and then, you know, if I increase 80, 90, 100, 110, it's just always squishing it in. It's that horizontal stretch with a scale factor that's pulling it in more. So what I would say is I would just say, you know, increase the ATT. Increase the ATT. So to, you know, for example, 90t or 100t, etc. That is the coefficient that kind of matters here. Cool, that is question 13, done. A company decides to manufacture a soft drinks can with capacity 500 ml. Company models the can in the shape of a right circular cylinder with a radius r and height h. In the model, they assume that the can is made from a metal of negligible thickness. Prove that the total surface area of the can is given by that. Cool. So we've actually done a disgusting questions video on this. It's basically to do with, we're going to eventually want to kind of minimize or maximize some quantity. So the first bit's a bit of algebra and using a bit of geometry and shapes and stuff, and then there'll be a bit of calculus thrown in the end. So let's have a think about this. Total surface area of the can. So we've kind of got a cylinder here, haven't we? So you're going to see an absolutely awful drawing of a cylinder right now from yours truly. So let's have a think about what's popping off here. Oh, gorgeous, isn't it? Right. So we've got a radius, haven't we? So bit of a radius kicking off here, and we've got a height. Okay, I can't even write the word h. H isn't even a word. What's going on? Right, okay. So there's kind of two variables here, isn't it? And it's saying, right, like, what's going on, the relationship between r and h? Can I maximize the volume? Can I minimize the surface area? Stuff like that. Now, we are given the volume. The volume is 500 milliliters. Okay. And then we want the surface area. So can we get any kind of equation given that we have this v equals 500? Well, if I was to work out the volume of this in terms of r and h, what would I do? I would take the cross-sectional area of this, which is pi r squared, and multiply it by the height. So I know that pi r squared h is equal to 500. Now let's separately try and work out the surface area of this thing. Well, it's kind of made up of 3 bits, isn't it? It's made up of the bottom, pi r squared, made up of the top, pi r squared, and it's made up of basically, it's all of this curved surface area, isn't it? If I take the circumference of this circle, it's almost like I'm taking that circumference and just stacking loads on top of each other, isn't it? So if I take the circumference of the circle and multiply it by the height, that's just going to get me that area going around. So the circumference of the circle is going to be 2 pi r. 2 pi r. And then I'm going to multiply that by h. Lost the plot on question 14. Right, so basically, now let's just see what we can do algebraically. This is going to be 2 pi r squared plus 2 pi r h, and that's it. But the answer that they have, you can see that they don't have any h's in it. So if I use the top equation to get h in terms of r, I can then sub that in. So equation 1 is going to imply that h is equal to 500 divided by pi r squared, and just stick that in the other one, right? So this is going to be 2 pi r squared plus 2 pi r, I can't believe I said h was a word, 500 over pi r squared. Hopefully this is going to be the right answer. So I'm going to get 2 pi r squared plus, right, what's kicking off? 2 multiplied by 500 is 1,000. Pi over pi, they're going to go. And then r over r squared, that's just going to be basically 1r on the bottom, isn't it? So is that the answer? Yes, sick. Okay, B. Given that r can vary, find the dimensions of the can, okay, yeah, that has a minimum surface area. So the reason we got this s just in terms of r is because it's now quite easy to differentiate it, isn't it? It's a bit more trouble when there's still an h there. So what I can do is I can say, look, ds by dr is equal to 4 pi r. And then this thing here is the same as 1,000r to the minus 1, isn't it? So differentiating that, I'm going to bring this minus 1 to the front. And then it's going to be r to the minus 2. Cool. Now, stationary points, right? Minimum, maximum, they're stationary points. We find stationary points by setting the derivative equal to 0. So I've got an equation, haven't I? I've got 4 pi r equals 1,000 divided by r squared. Just solve for r, so I'm going to multiply by r squared to get 4 pi r cubed equals 1,000. I'm going to divide by 4 pi to get r cubed equals 1,000 over 4 pi. And then I'm going to get r as the cube root of 1,000 over 4 pi. Cool, straight to your calculator to get the following. Cube root of 1,000 divided by 4 lots of pi. That gets me 4.3. I mean, it gets me something a bit more, so it gets me 4.30127 ... 4.3 sounds about good to 2 significant figures here. And I believe that is centimetres, 4.3 centimetres. Are we done? I don't think so quite yet, because it says find the dimensions of a can that has minimum surface area. Okay, so we know the radius, that's kind of one of the dimensions. We're going to need to know the height as well, aren't we? They're the two variables, radius, height. So if we get the height, we can work this out here. Look, h equals 500 over pi r squared. So I would then say, well, that means that h equals 500 over pi times this thing squared. But because I've got this in as ants on my calculator, the unrounded version, that's what I'm going to use. So I'm going to get it out, and then I'm going to say 500 over pi times ants squared to get me 8.6025, and again, to 2 significant figures, 8.6 centimetres. Cool, my handwriting gets worse as the paper goes on. Oh well. So, with reference to the shape of the can, suggest a reason why the company may choose not to manufacture a can with minimum surface area. Right, bit weird. Let's have a think. Okay, well, I suppose it says with reference to the shape of the can, and in the last bit of the question we worked out the dimensions. Obviously it's the dimensions of the can that determine the shape of the can. So a good place to start is probably looking at those numbers. So this says that r equals 4.3 and h equals 8.6. Well, if r equals 4.3, then the diameter is actually 8.6, isn't it? So it's 8.6 centimetres across. But then it's also 8.6 centimetres upwards, isn't it? So I don't know, you've got a bit of that going on. That's probably a bit weird, I think. The reason is, if you think of a can of Coke, right? It's usually not as tall as it is wide. You know, it's usually kind of quite thin and then goes up, doesn't it? So you can kind of hold it like that. But this is basically like, it's almost a cuboid, isn't it? It's as wide as it is tall. If you think about that, if you think of your kind of can of Coke was as wide as it is tall, it'd be pretty fat, wouldn't it? Right? So I think that's not very normal. You know, you probably won't be able to fit it in your hand. So I would just say, look, in this case, the can would be as tall as it is wide. I mean, first of all, it isn't really normal, so it's not really going to fit in with any of the other cans, is it? You're not really going to be able to stack a shelf with it nicely there if it's some fat can like that. And it probably wouldn't even be nice to kind of hold. Might even be, I don't know, too wide for our hands. Bit of a strange one there, but yeah, I suppose they're really kind of pushing this modelling real world vibe, aren't they? And that's what I'd say in the exam. Alright, 15, looks grim, I want to get this over with, so let's go. Figure 4 shows a sketch of the curve C with equation, all of that stuff. Point P with coordinates 4, 15 lies on C, line L is a tangent. Region R, shown shaded in figure 4, is bounded by the curve C, the line L on the y-axis. Show that the area of R is 24. Right, there's quite a lot kicking off here, isn't there? Best idea, get the diagram up, and then just kind of figure out what's kicking off. Like, what are we going to need here? We obviously want the area of this R. Problem is, it's not as simple as just kind of doing an integral or something. There's kind of a few parts here, isn't there? Let's think about if I was to kind of draw a line at P down here. If I was to integrate the curve C between 0 and P, which I believe the x-coordinate is 4, then it would get me everything underneath the curve and above the x-axis. So it doesn't get everything I want, and it gets some stuff that I don't want. But those two little things, can we kind of get them into it? Well, I think we can, because they're both triangles, aren't they? So if I was to call this maybe the red triangle, maybe call that area 1. And then if I have another triangle, which let's call the blue triangle, being all of this stuff, so kind of area 2, if I worked out the area of these two things and then, you know, had the black as area 3, then I think between all of those things I can work out the area of R. So, slow down, right? How am I going to get all of this stuff? I think I'm really going to want the equation of this tangent. And the reason is, I've got, if I had these points here, I can work out the area of these triangles. So if I get the equation of the tangent and then work out where it hits the axes, I think I'm good here. How do we get the equation of a tangent? Well, it's a straight line, so we need two pieces of information. M and an x1, y1. Do we have either of those? Well, we know it goes through P, doesn't it? Because it's a tangent at P. P is 415, so we've got one of them. But we don't have M, do we? Can we get M? I think we can. So, we differentiate. If we were to differentiate the curve here, we're going to get the gradient at each point. We can then substitute the point P in, and it's going to get us that gradient. Okay, so what we're going to do, we are going to bring the power to the front on each term and take 1 away from the power. So 3 over 2 minus 1 is 1/2. This is going to be a minus 9. The 11 is going to go away. Okay, that would tell me that my M is going to equal all of this stuff with 4 substituted in. Okay, so 4 to the half is 2 because a half is the square root. So I get 3 over 2 times 2, so the 2's cancelled, so I'm actually just left with 5 times 3 here. Still got the 9 on the end. 5 times 3 is 15, minus the 9, I'm going to get 6. That tells me that the equation of my line is going to be y minus y1, so y minus 15, equals m, 6, times x minus x1, which is 4. Clean him up a bit, so this is going to be 6x minus 24, and I'm going to bring this 15 over the other side, so it's going to be 6x minus 9. Okay, that is the equation of the tangent. Now, as I said before, it would be fantastic if I had this point and this point. So what I'm going to do, I'm going to sub x and y equals 0 in respectively to get where it hits the axes. So, in this equation here, x equals 0 implies that y is equal to 0 minus 9. So minus 9. Y equals 0 implies that 6x minus 9 equals 0. In other words, x is equal to 9 over 6 or 3 over 2. Okay, so x is 3 over 2, y is minus 9. Let's get them on the diagram. So I've got a 3 over, let's zoom in, why not? Here we go, 3 over 2 here, and then minus 9 here. Okay, so I can work out the area of this triangle, can't I? Because, let's go red here. It's half base times height. So the area of 1 is going to be a half times base, which is 3 over 2, times height, which, if that's minus 9, then the magnitude of the height of it is just 9, isn't it? This is going to be what? Well, what have I got on the top? I've got 1 times 3 times 9, which is 27. And on the bottom, I have 2 times 2, which is 4. Okay, so I've got one of the areas. Does that mean we're a third of the way through? Maybe, probably not, because I've not done any integration yet. Let's try and get the area of 2. How am I going to get that? Well, again, half base times height, right? So 2 is going to equal a half the base. If this is 4 and this is 3 over 2, then the length here is going to be the difference between them, isn't it? So it's going to be 4 minus 3 over 2. Height of this thing is going to be the y-coordinate of p, which is 15. So that is going to get me the area of 2. So stick it in your calculator. I'm going to get a half multiplied by 4 minus 3 over 2 multiplied by 15, which gets me 75 over 4. Okay, we're getting there now. So I've got 2, I've got 1, park them to the side. The last thing I need is 3, isn't it? This black area. So that is going to be the integral. It's going to be the area under the curve. So it's going to be the integral of C between 0 and 4, between these two bounds here. So that's probably going to be the meat here. So let's... here we go. Let's get cracking on that one. Right. So the area 3 is going to equal the integral between 0 and 4 of the curve C, which is 5x to the 3 over 2, minus 9x plus 11. Right, let's do it. I'm going to have square brackets because it's a definite integral. Add 1 to the power to get x to the 5 over 2. Divide by the new power, so multiply by 2 over 5. So obviously divide by 5 over 2, same as multiplying by 2 over 5. So 5 times 2 over 5, x to the 5 over 2, and then minus 9x squared all over 2, plus 11x. Okay. Limits go on the right. Now, what am I going to get when I sub 4 in? I'm going to get 5. So, okay, 5 times 2 over 5, the 5's cancel, which is fantastic. So, basically, I'm going to be left with 2 here. So, 2 times 4 to the 5 over 2 minus 9 over 2 times 4 squared plus 11 times 4. Now, I'm going to have a bracket here that I get from subbing in 0 to everything. But look, these are all polynomial terms. This is going to go to 0, this is going to go to 0, and this is going to go to 0. So that whole bracket goes to 0, which is the great thing about integrating polynomials when 0 is one of the limits. So I want to work this thing out, and then I think I'm close. So 2 multiplied by 4 to the power of 5 over 2 minus 9 over 2 multiplied by 4 squared plus 11 times 4 gets me 36. Meaning my total area, let's go back to this thing here, it's going to be area 3 minus area 2 plus area 1, okay? Because it's the black minus the blue plus the red. So 3 minus 2 plus 1. So it's basically going to be 3 and then minus 2 plus 1. Okay, so the 3 is 36. The 2 we know to be 75 over 4. And then the 3 is 27 over 4. Okay, so it's minus 75 over 4 plus 27 over 4. And let's hope, okay, so 36 minus 75 over 4 plus 27 over 4. And I really hope this is right. I get the final area to be 24. Here it is, last question. Let's have it. So, express 1 over p 11 minus 2p in partial fractions. Alright, I reckon I can do that. So what we're going to do, we're going to say that it is the same as some constant a over p plus some other constant b over 11 minus 2p. And what we need to do now is determine a and b. So we're going to multiply by everything on the bottom here, getting us 1 equals a. P is going to cancel. I'm going to be left with 11 minus 2p here, plus b, and then the same thing with the 11 minus 2p, so I'm left with a p. What I can now do is just substitute in values of p because it's equal to, I mean, technically it's an identity, isn't it? Because it's valid for all values of p, essentially. So I'm going to sub p equals 0 in, and the reason I'm going to do that, well, you'll see. So I'm going to get 1 is equal to 11a. That goes, and then that goes as well. So straight away I get a equals 1 over 11. I'm now going to sub in a value of p that's going to get rid of this, so I can get the value of b. And that is going to be, I believe, what's it going to be? Is it going to be 11 over 2? I reckon so. So that is going to get me 1 is equal to, 11 minus 2 times 11 over 2 is going to go to 0. So I'm going to get 11 over 2b. So b is going to be 2 over 11. Fantastic. So to kind of finish off, I'm going to get 1 over p times 11 minus 2p is the same as 1 over 11p plus 2 over 11 times 11 minus 2p. A lot of 11s flying about here. Okay, population of meerkats. What are they on about here? Population of meerkats is being studied. It's modeled by the differential equation 1 over 22p 11 minus 2. Okay, cool. Where p in thousands is the population of meerkats times t, measured in years, all of that stuff. Given that there were 1,000 meerkats in the population when the study began, determine the time taken in years for this population of meerkats to double. Okay, so if you've not yet worked it out, you're going to need to solve this differential equation, okay? I mean, it's 6 marks, so that's probably, putting you in that direction as well. But, if we want to find out different things, time it takes for population to double, all of that stuff, we're going to need a relationship between p and t that doesn't involve derivatives. In other words, we're going to want the solution of the differential equation. So, dp by dt is equal to 1 over 22 multiplied by p 11 minus 2p. Can we see anything that's going to help us from part A? Of course we can, but you knew that was going to be the case, didn't you? So we're going to separate the variables here. So all of this p stuff I'm going to bring down, okay? So I'm going to get 1 over p, 11 minus 2p, dp, and then I'm going to multiply both sides by dt. I'm going to get 1 over 22 dt. Now we can integrate both sides. And it's nice because obviously this integral's with respect to p, this one's with respect to t, and all my p's are here. Okay, so it's essentially just 2 different integrals, okay? Look at the one on the left. You really need to realise, wait a minute, isn't that exactly what I just did in part A? Yes, and this always happens, so please always be thinking about, wait, have I done anything in the previous parts of the question that are going to help me in this integral? Trust me, you will get asked it. So, obviously, they're going to want us to rewrite this as what we did in part A, okay? So, what we're going to get? We're going to get 1 over 11p plus 2 over 11 minus 2p dp is equal to 1 over 22 dt. Okay, I can integrate both of these terms on the left, but you look at these 11s, right? I've got a 22 here, which is 2 lots of 11. Why don't I just multiply everything by 11 here? I'm allowed to do that because constants, you can kind of take them in and out of integrals. They're not going to affect actually how you do the integration. So I am allowed to just multiply everything by 11 here. That's going to make my life a bit easier, isn't it? Because I'm going to get 1 over p plus 2 over 11 minus 2p equals 1 over 2. So that makes my life a lot easier. Now I can integrate the left-hand side. 1 over p integrates to ln p. Now, this thing here, so I'm going to take the 2 outside. Now, if you want to do this longhand, just let u equals 11 minus 2p. What I do, though, is I say, look, this is linear, so I can treat this as if it's just a p, for example. So, like, ln p would, 1 over p would go to ln p, so 1 over 11 minus 2p is going to go to ln of 11 minus 2p. But when I do that, I need to divide by the derivative of this transformation. So this transformation in this case is 11 minus 2p. The derivative of that is going to be minus 2, so I need to make sure I divide by that minus 2. If you want to prove this to yourself, differentiate this and you'll get that. And the reason you'll get that is because when you're using the chain rule, we need to multiply by the derivative of this transformation. So when we integrate, we need to just divide by the derivative of the transformation to outdo it. Cool. I'm then going to have a half t, and I've explained this in other videos, so I'm not going to go into too much detail about it now, but I only need a constant on one side. Doesn't matter where you put it, let's put it here. Okay, so it looks like part C we're then going to be rearranging this for p. So I suppose they don't really care about doing that yet. It says determine the time taken in years for this population of meerkats to double. So, okay, well, there's a few things kicking off here. There were 1,000 meerkats when this study began, so I think it would be a good idea to put those numbers in first, because I'm going to get this C here. In other words, when t equals 0, p was not 1,000, p was 1. Because look, p in thousands, and there were 1,000 at the start. So how many thousands were there at the start? One of them. Cool, okay, let's put these numbers in and see what we get. So I'm going to get ln 1, and then plus 2 over minus 2, that's minus 1, isn't it? So minus ln of 11 minus 2, 2 times 1, equals 0 plus c. So c is going to equal, ln of 1 is 0, so this is going to be minus ln of 9. Cool, c is minus ln of 9. So let's put it in here and see what we get. So we're going to get ln of p, and then that's minus ln of 11 minus 2p equals a half t minus ln of 9. Cool, okay, we're getting there. So why don't we, well, for this part of the question, they just want me to get this time. So because I've already kind of got time here, let's just sub in the population. So population to double. In other words, what is t when p equals 2? So sub in p equals 2. And I'm going to get the following. Ln 2 minus ln of 11 minus 4, 2 times 2, is equal to a half t minus ln of 9. Okay. So, what we're going to get, ln 2 minus ln 7, I'm going to add that, so I'm going to get plus ln of 9 equals a half t. Let's get these lns together. So technically, we can kind of go to our calculator, but I want you to practice your log loss. So, now, these two are going to get together by multiplying, because that's the addition law, and then I'm going to divide by this 7. And then that's a half t, so multiply both sides by 2 to get t. So t is going to equal 2 ln of 2 times 9 over 7, which is going to get me 1.8889 and then time taken in years. So it's basically that many years. Maybe you can go 3 sig fig if you want, so that would be 1.89 years. 3 sig fig. Let me just check if t is measured in years. T is measured in years, yeah. So always just make sure they don't want to do, any time unit conversions. Cool, okay, so we've got that. Now, part C basically now wants me to rearrange. So this is the equation I want to use here. Essentially, I just want to rearrange this for p. So, first thing I'm going to do is I'm going to put these logs together on the left-hand side. So I am going to say that this is ln of p over 11 minus 2p. I'm also going to add this ln of 9. So this is going to be plus ln of 9 is going to equal a half t. So I want to get rid of these logs. Okay, maths times. Let's get these logs together first of all. I can't get rid of the logs now. I just want a single log on the left-hand side. So again, I'm going to multiply these things to get ln of 9p over 11 minus 2p is equal to a half t. Now I can undo the logs. So if I do e to the power of both sides, well, on the left-hand side, it's just going to cancel. So I'm literally going to be left with 9p over 11 minus 2p. And then on the right-hand side, I will have e to the power of a half t. Right, what do we do now? I need p on its own. So I'm going to multiply by all of this stuff. So I'm going to get 9p equals e to the half t. My voice is going. 11 minus 2p. Multiply out. There's a lot kicking off here. E to the half t. Well, 11 of them. And then minus 2p e to the half t. Okay, I want all the p's on one side together so I can get it on its own. So I'm going to add this term to the left. So I'm going to get 9p plus 2p e to the half t equals 11e to the half t. I can now factorize out a p here, because that's what my goal is, isn't it? To get 9 plus 2e to the half t equals 11e to the half t. I can feel the end, I can feel it. Now I divide by all of this to get p equals 11e to the half t divided by all of this stuff. So 9 plus 2e to the half t. I've got p, but I'm going to just check over exactly the form they want it in. Because look, they want a over b plus c e to the minus a half t. So it's quite interesting, isn't it? Because I've not got just a constant on top. But there's something I can do here. If I was to divide both top and the bottom of this fraction by e to the half t, what would happen? So let's do it longhand. So obviously if I'm dividing by this, that's just going to cancel. So I'm going to be left with 11 on top. I'm going to be left with 9 divided by e to the half t. And then plus, well, those e to the half t's would cancel, right? Plus 2. Now this is a really common idea. And the reason is, this doesn't look too nice, but there is a nicer way we can write this. Because if I'm dividing by this power here, that is the same as e to the minus a half t. So now compare it with what they want. Well, they want a over b plus c e to the half t. So in other words, if I was to just rewrite these the other way around, 11 over 2 plus 9e to the minus half t, that would get my a as 11, b is 2, and c equals 9.